For the code line print, number of rows edf.shape. Explanation, speaker notes. This line prints the number of rows in the dataset. The variable df represents the dataset stored as a table. The command shape gives us the size of the dataset. It returns two numbers, the number of rows and the number of columns. When we use shape followed by 0 inside the brackets, we select the first number. This number represents how many observations or measurements exist in the dataset. In our dataset, each row represents one measurement taken at a specific time. Next line of code print, number of features, df.shape. Explanation, speaker notes. This line prints the number of features in the dataset. Features are simply the columns of the dataset. Each column represents a variable or measurement. For example, some columns represent pollution levels, others represent temperature, humidity, or sensor readings. When we use shape followed by 1 inside the brackets, we select the second number returned by the shape command. This number represents how many variables exist in the dataset. Next line of code print, start time, df, date time, min. Explanation, speaker notes. This line prints the earliest time recorded in the dataset. The code looks at the column called datetime, which contains the time of each measurement. The function called min finds the smallest value in that column. For time values, the smallest value corresponds to the earliest moment when data was recorded. This tells us when the dataset begins. Next line of code print, end time, df, date time, max. Explanation, speaker notes. This line prints the latest time recorded in the dataset. The code again looks at the datetime column. This time the function called max finds the largest value in that column. The largest value corresponds to the most recent measurement in the dataset. By comparing the start time and the end time, we can understand how long the dataset covers. Next line of code print, df, datetime, .diff, .value, dux counts, it head. Explanation, speaker notes. This line helps us understand the sampling frequency of the dataset. Sampling frequency tells us how often measurements were recorded. First, the code calculates the difference between consecutive time values in the datetime column. This means it measures the time gap between one observation and the next. Then the program counts how many times each time interval appears. Finally, we display the most common intervals. If the dataset was collected consistently, we should see that measurements occur at regular intervals, such as every hour. Understanding the sampling frequency is important when working with time series data because it tells us how the data evolves over time. Part 2, Statistical Profiling, Step 12, Basic Statistics, first line of code, print, df describe. Explanation, speaker notes. This line generates a statistical summary of all numerical columns in the dataset. The function describe is a built-in function in the pandas library that quickly calculates several important statistics. When we run this command, Python computes the following values for each variable: count, how many valid values exist in the column mean, the average value mean, the smallest value observed 25% percentile, the value below which 25% of the observations fall, 50% percentile, median, the middle value of the data, 75% percentile, the value below which 75% of observations fall, max, the largest value observed, standard deviation, a measure of how much the values vary around the average. This summary helps us quickly understand the distribution and variability of the data. For example, if the mean and median are very different, the tar might be skewed. If the standard deviation is large, the values vary significantly. This is usually the first step in exploratory data analysis because it allows us to detect anomalies, outliers, or unusual ranges. According to the official pandas documentation, describe provides descriptive statistics that summarize the central tendency, dispersion, and shape of a dataset's distribution. Step 13. Skewness and kurtosis, next line of code. Print, skewness. Explanation. This line simply prints the title, skewness, to make the output easier to read. It separates this section from the previous statistics. Next line of code print, df, unskew, numeric only, true, explanation. This command calculates the skewness of each numerical variable in the dataset. Skewness measures how symmetric the data distribution is. A value close to 0 means the distribution is symmetric. A positive skewness means the distribution has a longer tail toward larger values. A negative skewness means the distribution has a longer tail toward smaller values. In practical terms, positive skew, many small values and few very large values; negative skew, many large values and few small values. Skewness helps identify whether the dataset follows a normal distribution or if it contains extreme values. The Pandas documentation defines skewness as a measure of asymmetry in a distribution. Next line of code print, kurtosis. Explanation. This line prints a label indicating that the next results correspond to kurtosis values. This helps separate the results in the output. Next line of code print, df kurtosis, numeric only, try true. Explanation. This command calculates the kurtosis of each numerical variable. Kurtosis measures how heavy the tails of a distribution are compared to a normal distribution. In simple terms, it tells us how likely the dataset is to contain extreme values or outliers. If kurtosis is close to 0, the distribution behaves similarly to a normal distributee. Ion positive. The distribution has heavier tails and more extreme values, negative. The distribution is flatter with fewer extreme values. High kurtosis indicates a higher probability of rare but very large deviations. According to statistical literature, kurtosis describes the tailedness of a probability distribution. Step 14. Interquartile range, IQR. Your code for this step will likely follow in the next section. Concept explanation, speaker notes. The interquartile range, often abbreviated as IQR, measures the spread of the middle 50% of the data. It is calculated as IQR eng Q3, Q1, where Q1 is the 25th percentile, Q3 is the 75th percentile. The IQR is useful because it helps detect outliers. Any value that lies far outside this middle range may be considered an unusual observation. IQR is widely used in exploratory data analysis because it is robust to extreme values. In this section, we explore the dataset using different visualization techniques. Visualization helps us understand patterns, relationships, and anomalies in the data. First, we create a histogram of the CO concentration. The command df CO GT histbins TI30 creates a histogram with 30 bins. A histogram shows how frequently different values occur in the dataset. In our case, it allows us to observe how carbon monoxide concentrations are distributed. If most values appear in a small range, the histogram will show a tall cluster of bars. If the values are spread out, the bars will appear more evenly distributed. Histograms are widely used in exploratory data analysis because they help reveal the shape of the data distribution. According to the Python visualization documentation, histograms are useful for understanding the frequency distribution of numerical variables. Next, we use a boxplot to detect outliers. The command sns.boxplot xsdf cogt creates a boxplot of carbon monoxide concentration. A boxplot summarizes the data using 5 key statistics: minimum first quartile, median third quartile, maximum points that appear far outside the box are considered potential outliers. This visualization is very useful for quickly identifying unusual measurements. According to Seaborn documentation, boxplots visualize the distribution of data and highlight potential outliers. Then we create a scatter plot. The command plt.scatter df NOx gt df NO2 gt plots nitrogen oxides against nitrogen dioxide. Each point represents a measurement in the dataset. Scatter plots are useful for detecting relationships between two variables. If the points form a clear pattern, it may indicate a correlation between the two pollutants. Scatter plots are commonly used to explore relationships in environmental and scientific datasets. Next, we compute a correlation heat map. The command sns.heatmap gdf.core numeric only true cmrp port coolwarm calculates the correlation between all numerical variables and visualizes the results as a color matrix. Correlation values range between 1 and 1. A value close to 1 indicates a strong positive relationship. A value close to 1 indicates a strong negative relationship. A value near 0 suggests little or no relationship. The heat map makes it easier to visually identify strong correlations between variables. Heat maps are widely used in data science to summarize relationships across many variables at once. Next, we examine average CO concentration per hour. The command df.groupByDF datetime dt_hour co_gt mean groups the data by hour of the day and calculates the average CO concentration for each hour. This helps us understand how pollution levels change throughout the day. The resulting bar plot allows us to see which hours tend to have higher carbon monoxide levels. Such patterns are often linked to traffic activity or industrial operations. Next, we visualize CO concentration over time. Using a time series plot, we place time on the horizontal axis and carbon monoxide concentration on the vertical axis. This visualization helps us observe long-term trends and fluctuations in pollution levels. Time series analysis is widely used in environmental monitoring and forecasting. Then we compute a rolling average. The command df co_gt rolling 24 mean calculates the moving average over 24 observations. This smooths short-term fluctuations and highlights long-term trends. Rolling averages are commonly used in time series analysis to reduce noise and reveal underlying patterns. Finally, we generate a pair plot. The command sns.pairplot df co_gt nox_gt no2gt t creates scatter plots for every pair of selected variables. This allows us to examine multiple relationships at once. Pair plots are particularly useful when exploring environmental datasets because they reveal possible interactions between pollutants and temperature. In this slide, we visualize different aspects of the air quality dataset using several plots. Let us begin with the scatter plot in the upper left corner. This plot shows the relationship between nitrogen oxides and nitrogen dioxide. Each point represents one observation recorded by the sensors. We can see a clear upward pattern in the points. This means that when nitrogen oxides increase, nitrogen dioxide also tends to increase. This indicates a positive relationship between these two pollutants. Such a relationship is expected because both gases are typically produced by similar sources such as traffic emissions and industrial combustion. Scatter plots are very useful when we want to examine whether two variables move together. Next, we look at the histogram in the lower left corner. This histogram shows the distribution of carbon monoxide concentrations. Each bar represents how often a certain range of values appears in the dataset. We observe that most measurements occur at lower concentration levels, while fewer measurements appear at higher values. This tells us that high carbon monoxide levels occur less frequently, but they still appear in the dataset. Histograms help us understand the overall shape of the data distribution and whether values are concentrated in a specific range. Now let us look at the correlation heat map in the center. This visualization shows the relationship between several variables in the dataset. Each square represents the correlation between two variables. Warm colors indicate a strong positive relationship, meaning the variables increase together. Cooler colors indicate a weaker or negative relationship. By looking at this heat map, we can quickly identify which environmental variables are strongly connected to each other. This helps us understand how different pollutants and environmental factors interact. Finally, on the right side, we see a box plot used for outlier detection. The box plot summarizes the distribution of carbon monoxide values. The line in the middle of the box represents the median dx, which is the middle value of the dataset. The box itself represents the interquartile range, meaning the middle 50% of the observations. The lines extending from the box represent the typical range of the data. Values that appear far away from this range may be considered outliers, meaning unusually high or low measurements. These outliers could indicate unusual pollution events or measurement anomalies. Together, these visualizations help us understand three important aspects of the dataset: the distribution of pollution levels, the relationships between pollutants, and the presence of unusual measurements. In this section, we perform time-based feature engineering. Feature engineering means creating new variables from existing data in order to make the dataset more informative for analysis and machine learning. In our case, the dataset contains a datetime column, which represents the exact time when each measurement was recorded. From this timestamp, we can extract several useful time features. First, we extract the hour of the day. This creates a new column called hour. The hour tells us when the measurement occurred during the day, from 0 to 23. This feature is important because pollution levels often vary throughout the day, especially during traffic peaks. Next, we extract the day of the month. This creates a column called day. This allows us to analyze whether pollution patterns change across different days. Then we extract the month. This creates a new column called month. The month helps us identify possible seasonal patterns in the data. For example, pollution levels may change depending on weather conditions or heating usage during winter months. After that, we extract the weekday. This variable indicates the day of the week, ranging from Monday to Sunday. This helps us examine whether pollution patterns differ between working days and non-working days. Next, we create a weekend indicator variable. If the day corresponds to Saturday or Sunday, the value becomes 1. Otherwise, it becomes 0. This binary variable allows us to easily compare pollution levels between weekdays and weekends. Such comparisons are useful because traffic and industrial activity often change during weekends. After creating these features, we compute the average pollution level for each hour of the day. To do this, we group the dataset by the hour variable and calculate the average value of the numerical columns. This gives us a table that shows the average pollutant level for each hour. Finally, we detect the peak pollution hour. We look specifically at the carbon monoxide variable. The function identifies the hour that has the highest average CO concentration. This helps us determine when pollution tends to reach its maximum during the day. Often these peaks correspond to rush hours, when vehicle emissions are highest. By extracting and analyzing these time-based features, we can better understand daily patterns in air pollution, which is an important step before building predictive models. In this final step, we perform feature engineering. Feature engineering means creating new variables from the existing data in order to capture additional information that may improve analysis and prediction models. Instead of relying only on the original measurements, we combine variables to create more informative indicators. The first feature we create is the CO to NOx ratio. This ratio compares the concentration of carbon monoxide to the concentration of nitrogen oxides. Ratios like this are useful because they help us understand relative pollutant behavior, rather than looking at each pollutant independently. For example, changes in this ratio may indicate different emission sources or combustion conditions. The second feature is a pollution index. This index combines several pollutants: carbon monoxide, nitrogen oxides, and nitrogen dioxide. We calculate the average of these values to produce a single indicator that represents overall pollution intensity. Using an index simplifies analysis because we can track one combined measure instead of many separate variables. The third feature is a thermal discomfort index. This variable combines temperature and relative humidity. Higher temperatures and higher humidity levels can increase the feeling of discomfort in the environment. By combining these two variables, we create a simple indicator that reflects environmental comfort conditions. Next, we create a high pollution flag. This is a binary variable. If the pollution index is higher than a typical threshold, the value becomes 1 ton, meaning high pollution. Otherwise, it becomes 0, meaning normal conditions. Binary indicators like this are very useful in machine learning, especially for classification tasks, where the goal is to detect critical conditions. Finally, we compute a rolling pollution mean. This calculates a moving average of the pollution index over 24 observations. Rolling averages smooth short-term fluctuations and highlight longer-term trends in the data. This helps us observe gradual changes in pollution levels rather than focusing only on momentary spikes. Through these engineered features, we transform the dataset into a richer representation of the environment. These new variables capture relationships, trends, and conditions that are not directly visible in the raw data. This step is essential before applying predictive models or deeper analytical techniques.